am R. Prabha, Assistant Professor in the Department of ECE, SNS College of Technology. In this lecture series, we are going to see the topic on magnetic field intensity and flux density. The magnetostatics, the scientist Oersted discovered the relation between electric and magnetic fields in 1820. He stated that when the charges are in motion, they are surrounded by a magnetic field. The charges in motion constitutes an electric current, thus the current carrying conductor is always surrounded by magnetic field. If such a current is steady and it is time invariant, then the magnetic field produced is steady magnetic field. The DC is a steady flow of current, hence magnetic field produced by a conductor carrying a DC current is called steady magnetic field. So the study of steady magnetic field existing in a given space produced due to the flow of direct current through a conductor, and it is called as magnetostatics. So this sources of magnetostatic field is from constant current, from permanent magnet, and electric field changing linearly with time. And we want to see the analogous between electrostatic and magnetostatic fields is the electrostatic, the source is the static charge, but in the magnetostatic it is a steady current. And if we consider the field, electrostatic, it is electric field intensity, and the flux density or displacement density vector D. And in magnetostatic, the field is called magnetic field and the flux density, magnetic flux density, denoted by B vector. Here the field quantities have both direction and magnitude. So the field intensity and flux density in both electrostatic and magnetostatic are vectors. And there are two important factors involved in electrostatic and magnetostatic is, one is the electrostatic is the permittivity and magnetostatic is the permeability. And the Maxwell's equation for electrostatic is del dot D is equal to rho V and del cross E is equal to 0. And for magnetostatic, it is del dot B is equal to 0, del cross H is equal to J vector. And if we talk about potential, the scalar V with electric field intensity E is equal to minus del V, that is negative gradient of V is equal to electric field intensity. And here for magnetostatics it is B vector is equal to del cross A vector. And energy density for electrostatic, W E is equal to 1 by 2 epsilon E squared. And for magnetostatic, the energy density is called as Wm, and it is 1 by 2 mu H squared. And now we see the magnetic fields and its properties. So consider a permanent magnet has two poles which are called as N and S. The region around the magnet within which the influence of magnet can be experienced is called a magnetic field. So such a field is represented by imaginary lines around the magnet, which are called magnet's lines of force, and which was introduced by Michael Faraday, and the direction of lines always from north to south. And these lines of force are also known as magnetic flux lines. So every magnetic flux line starting from north pole must end at south pole and complete the path from south to north internal to the magnet. So the magnetic flux lines always exist in the form of closed loop. So the diagram shows the magnetic lines of force or flux lines. They start from north to and end towards the south, and this is the flux lines in a permanent magnet. And now we are going to see the magnetic field due to current carrying conductor. So considering a conductor, straight conductor, which carries a direct current which produces a magnetic field around it all along its length. So here the lines of force, in this case in the form of concentric lines in the places at right angles to the conductor. So this can be experienced by the diagram, and there is a straight conductor. Magnetic flux lines are perpendicular to the direct current, direction of the direct current, and we have a plane at right angle to the conductor. So we have a right hand thumb rule which is used to determine the direction of magnetic field around a conductor which carries a DC current. So according to the right hand thumb rule, if we hold the current carrying conductor in the right hand such that the thumb pointing in the direction of current and parallel to the conductor, when curved fingers point in the direction of the magnetic field around it, and thus the magnetic lines of force, that is the magnetic flux, always forms a closed loop, exists in the form of concentric circles around a current carrying conductor. So the total number of magnetic lines of force is called a magnetic flux, and it is denoted by phi, and it is measured in Weber. 1 Weber means 10 power 8 lines of force. So, and for strongness of the magnetic field, a quantitative measure is given by magnetic field intensity or the magnetic field strength, which is denoted as by H, and it is measured in amperes per meter or amperes turn meter. It is a vector quantity. This is similar to or analogous to electric field in electrostatics. And another important parameter in magnetostatics is the magnetic flux density. So the total magnetic lines of force or magnetic flux crossing a unit area in a plane at right angles to the direction of flux is called magnetic flux density, denoted by B vector, which is also a vector quantity measured in Webers per square meter, or another unit is Tesla, which is similar to the displacement density vector D in electrostatics. And we have an important relationship between electric field and magnetic field, and similarly the magnetic flux density and the field intensity are related with each other as B is equal to mu into H. Here B is the flux density, H is the field intensity, and the mu is called as permeability, and this is equal to mu naught into mu r. Here mu r is equal to 1 for non-magnetic materials, and for like free space, and mu naught is permeability of free space. And assessment, the H quantity is analogous to which component the following? Answer is E. Identify the following is the unit of magnetic flux density is Tesla. References. Thank you.